And everybody can see my slides now?
Yes, you're ready. Yeah.
Great. My name is Jon McCandless, and I'm the CEO of Gallox and Semiconductors. And we're using the next generation power electronic semiconductor to bring about a revolution in efficiency throughout the entire grid. So what we do is improve the transistors and diodes within power electronics. So have you ever wondered, why does your computer charger get hot? Why does it feel hot to the touch? And the reason for that is because of inefficiencies that exist within the circuit. So inside your computer charger is a circuit that looks like this. It goes from AC to DC, and it reduces the voltage from 112 volts down to, say 12.5 volts or whatever it may be. And it's comprised of many diodes and many transistors, along with capacitors and inductors. While each transistor is and diode is efficient, when you have them all together, the efficiency is below 90%. And throughout the grid, from the time energy is produced to the time it charges your computer, you've lost more than 20% of the energy due to these power conversion losses. And so regardless of whether the energy is created by conventional sources from a coal or natural gas facility, or whether it's produced by green energy, wind or solar, to the time it goes through the grid, to the time it charges your car, powers the lights in your office, etc. It's gone through dozens of these conversion steps. And as I said, the cumulative effect is that more than 20% of the energy is lost. And this is becoming a bigger problem because by 2030, the National Renewable Energy Lab projects that over 80% of all power electronics will go through, of electricity will go through power electronics. So it's a growing issue. So to address this, we're using gallium oxide. Gallium oxide has, special, unique material properties that enable it to be scaled down in size. And when you shrink it down in size, it becomes more efficient. So the relative size is proportional to the on resistance of the device, and the resistance is proportional to the inefficiency. So this is just a pictorial representation of, if you use silicon carbide, which is kind of the incumbent power electronics material, and gallium oxide. And so because you get extreme scaling in size, you can get an extreme scaling in the efficiencies. So the markets that are really appealing for this are EV charging stations. So this would be, high voltage. You want to make your charging station smaller, more compact, and then also go to higher powers to reduce charging times. For data centers, we all have heard of the energy apocalypse thanks to data centers and the CO2 emissions. So can we make the power conversion processes more efficient? And so these are examples of, moderate to high powers, and you don't really care about the size. Size matters, but it's not critical. For drones, aircraft, and satellites, you care about the power density. These are relatively low power compared to the other use cases, but you need to have the power in a really small package, and so you need high power density. By going to smaller, lighter power systems, that increases the range of your drone, it reduces the weight and reduces the cost to launch a satellite, etc. And then long term, it would be to affect the entire grid. And so this would be going to much higher voltages, tens of thousands of volts, and you could really then take a big bite out of the losses at the grid level. Diving into the data centers a little bit more, this is from McKinsey, or maybe BCG rather, and that by 2030 within the United States they project that almost 400 terawatt hours of energy are going to be consumed a year by data centers, which is equivalent to 40 million homes worth of energy. And so how can we try to make these more efficient and consume less energy? If we look at a breakdown of how energy is spent within a data center, you can see that part of it, in this case, 36% is to the equipment, and then 64% is for the facility. As you can see, the dominant contributor to the facility energy consumption is cooling, about 50%. Power electronics, and so that's what we're talking about, power electronic losses, that's 11%, and lighting. Uh, Within data centers, the way you evaluate efficiency is PUE, and that's just the total energy consumed, this entire pie chart, divided by this, what is actually going to the IT compute. So in this case, it's 36%. And that then gives you the PUE, which represents efficiency. So in a perfect situation where you had no cooling, no power conversion losses, no lighting expenses, you would have a PUE of 1. This is a plot showing if your entire data center used the silicon carbide, which is not true. It's, they use half silicon carbide, half silicon. But if they used all silicon carbide, and these were their current PUEs, with gallium oxide, this would be the reduction you would achieve. So for example, if the PUE is 1.4, with gallium oxide, it would be reduced to just over 1.3 for the PUE. If, as I said, in data centers today, they use silicon, which makes gallium oxide even a stronger case for gallium oxide. It's some combination of silicon and silicon carbide. In terms of economic savings, this is the size of the data center in terms of megawatts and as a function of what the data center's PUE is. And so when you're looking at hyperscalers, kind of in the future, 600 to 1,000 megawatts, the PUE is between 1.1 and 1.2. You can see that the savings is, in the range of 6 million per year per data center. Gallium oxide, I've been talking about silicon carbide. Silicon carbide has not gained widespread usage because of its cost. I was talking with some people at Siemens, and they had said to me, we haven't used silicon carbide because it's just too expensive. Now we are forced to because of the performance requirements. I think maybe it wasn't Siemens, it was another company rather. But anyways, one of the major players. And they said, we're now having to start to use silicon carbide because we're forced to because silicon can't support the requirements, but it's really expensive. So gallium oxide, in addition to being better from a performance perspective, can also be significantly cheaper. This has to do with how the materials are growing, and I'd love to talk about it later, but it's really beyond the scope of this discussion. But this is from the National Renewable Energy Lab, where they talked about theoretical costs of gallium oxide versus silicon carbide. So gallium oxide is $916, whereas gallium oxide could be $283. Basically a third of the cost for a wafer. In terms of the market size, the immediate market is a $6 billion plus market for discrete wideband gap semiconductors, and it's a growing market, annual growth rate of 35%. Long term, able to then build into the power inverter market, which is a much larger $100+ billion market. What we're currently working on is we're working on thermal management, vetting foundry and packaging partners, device engineering. We're performing circuit demos so we can get, rather than just about the device performance, talk about what does that mean at the circuit level, and have been making great strides. Our team, I founded the company. I earned my PhD at Cornell in 2023. Devdeep Jena and Grace Shing are faculty here at Cornell and are, the foremost authorities in ultra-wide bandgap semiconductors and real pioneers in the field of gallium oxide. And we've got a couple advisors, Bruce Fishbein, Rob Scharfen. We've just brought on another advisor who's an expert in the circuit area. Bruce was an executive at AMD and then at Cavium, which was acquired by Marvell, and has a lot of executive experience in both industry as well as in startups. To date, we've raised almost $1 million in grants, and we'd like to thank Ignite for supporting us. We're recipients of Breakthrough Energy Fellowship, NSF, SBIR, Air Force, I-Corps, and we were just named a global finalist for Hello Tomorrow. So if any of you are going to be in Paris in March attending Hello Tomorrow, I look forward to seeing you then. We've had multiple multinationals contact us wanting to evaluate and get demo products, and so we've been getting a lot of momentum. What we're currently doing, we're currently fundraising. The fundraising will go for device engineering, expand team, IP investments, and expanding our testing capabilities. We're also looking for strategic partners and expanding our advisory board. So with that, I'd like to thank you all, and I'll take any questions.
Thank you, John. Let me see. There is a question for John. Where does your gallium supply come from? Roughly 98% of the world's gallium comes from China, which recently banned the export of gallium to the US.
Yeah.
Good question.
Yeah. So
Very-
the wafers, yeah. So there's some mining, So it's a longer question, but so first off, gallium is used in gallium nitride and gallium arsenide. These have, are established markets and and have economic and military value. And so, the U.S., it's in their interest to ensure gallium supplies. There are mines coming online in Canada and Australia to help ease that. And with talking with some advisors who are investment bankers in this space, their thought, we'll see, is that the Chinese export ban is really as a bargaining chip with the U.S. But so right now, yeah, gallium prices have gone up about 60%. We haven't seen any rise. There's not been a substantial rise in wafer costs. And in fact, wafer costs are dropping. But long term, getting to that number I quoted of 216 per wafer will of course depend on gallium mining. But like I said, there are some mines coming online to hopefully ease some of that pressure.
Okay. Yeah. Thank you. There's a question. Is the efficiency improvement from reduction in drain source resistance or faster switching speed?
Yeah. So it's drain source resistance. By going to faster switching, you will increase the losses, right? So in a transistor, you have switching losses and conduction losses. Switching losses go up with the frequency. But we are able to, so we can go to higher frequencies, which would increase the losses, but then that increase in loss is offset by a reduction in the source drain conduction losses. Mm-hmm. So depending on what you want to do, if you want to stay at the same frequency, then we can make our device smaller and more efficient. If you want to go to higher frequencies, then we can go to higher frequencies without taking a hit on overall efficiency.
Mm-hmm. Mm-hmm. Okay, money question from Josh. How much are you raising? Do you have quantitative goals associated with the use of raised funds?
Yeah, so I'd love to talk with you offline, but it's in the about $3 million round.
Yeah, definitely. Would be great if you could connect with Josh and others. I think that concludes our. What's the word here? Breakout rooms. This platform uses a different language. Thanks again to all the presenters. Thank you, John. Thanks for the questions.